So, last day, we started saying that it turns out that magnetism and electricity are two sides of the same coin. We said that they're a force, a unified force that we call electromagnetism. We said that if you have an electric field... Oh, we got a special visitor. Going to pause the video for a second. So last day, we said that it turns out electricity and magnetism are part of the same force. We call it electromagnetism. I think I told you that if, for example, you have an electric field oscillating in this direction, sorry for you, those of you on YouTube, you'll have a magnetic field oscillating at right angles to it. We talked about how because electromagnetism are one and the same force, that a current carrying wire will create a magnetic field. Well, first of all, we talked about magnetic field lines. We said that magnetic fields don't come in charges, they come in poles. We had North Pole, we had South Pole, and because it was a field, we had to define the direction. What was the direction for magnetic field? We said it always points from north to south. And then I said, or it points in the direction that a compass needle will point. That's how we detect magnetic fields. We use a compass needle. And then somebody said, wait a minute, Mr. Dewick, are you telling me that a compass points south? I said, yes, it does. And someone tried to say, no, Mr. Dewick, I'm pretty sure compasses point north. That's what my daddy taught me when I was looking at... No. Compasses point south. And the reason they point south is inside the Earth. That's the magnet inside the Earth. At the North Geographic Pole, at what we also call, unfortunately, the North Magnetic Pole, there's a South Magnetic Pole down there. We talked about how for our three-dimensional drawings, we're going to use an X to show the tail feathers of an arrow going into the page. That'll be our symbol for into the page. We're going to use a dot coming out of the page towards us as though the point of an arrow is coming towards us. We're going to start to do three-dimensional pictures, especially today. And then we started to talk about magnetic field direction. We learned the first right-hand rule. We said if you point your right thumb... I said if you want to get these wrong, hold your right hand in really close. You want to get your hand away from your body. We said if you point your thumb in the direction of current, your fingers will curl in the direction of the magnetic field. Then we introduced the concept of an electromagnet, a solenoid, to you. And we said if you hold the solenoid in your hand and curl your fingers of your right hand in the direction of the current going through the wires, your thumb points to the North Pole outside of the solenoid. There is a third phenomena as well. If you have a wire carrying a current through a magnetic field, so here is a wire, I guess there's the battery, so I guess the current is going in this direction, yes? What do those dots mean? I sketched this by hand. Those dots are meant to show that the magnetic field is coming in which direction? Okay, so if you want to, you can draw a little arrow and label it capital B with a vector. That's the B field, the magnetic field. That magnetic field will exert a force on the moving charges within the wire. Moving charges in a magnetic field feel a force. I'll show you a video of that in just a second. I have an apparatus as well, but I haven't had a chance to set it up because I lost my prep yesterday. How do you find the direction of the force? Put your pencils down. This is by far the trickiest one. It is still right hand. You point your thumb in the direction of the current. Okay? And then hold your hand like you're going to high-five somebody. You point your fingers in the direction of the magnetic field, which for all of you means you're going to be now pointing behind you like this. Your palm points in the direction of the force. That wire is going to feel a force down the page. We're going to practice this a whole bunch. So, to find the direction of the force, you point the thumb of your right hand in the direction of the conventional current. You point your fingers, like you're high-fiving, in the direction of the magnetic field, and your high-five palm points in the direction of the force. This is the direction of the force that the wire will feel. So, in the above example, the net force would be down. Now, if you find you're having to contort your body, rotate your piece of paper 90 degrees and try again. Often then you'll find, oh, now it matches up with my hands and I can figure it out. Here at example 7, it looks like, oh, here's the wire. Which way is the current flowing in this wire? Into the page. So all of you point your right thumbs into the page, into your page, so you're all pointing it down at your desk. What direction is the magnetic field? The magnetic field is to the left. You know what? For me, I would be pointing my hand like this, I think. Yes? So, Mud's totally lost because he's got his fingers like this. You want your hand like you're high-fiving. Hand out, okay? So let's do it up here, first of all, on the board. I would say to myself, thumb going into the board. Yes? Magnetic field, which way? This way. So I just got to do that. Reach across my body. Which way is my palm pointing? All of you are following along and playing along with me at home. Nick. So you ready? Start over. Thumb into the page. Which way is magnetic field pointing? To the left? So how can I point my fingers to the left? Go gadget arms. I got to go to this side. Which way is my palm pointing? This is going to feel a force up the page. Now, if it was sitting on my desk, I would go, okay, thumb into the page. Yeah, I would just kind of bend my hand like that, and I still get up the page. Page, not like this. Hands like this, always. Yeah, but don't even, if you start doing this, you've added a 90-degree bend to your fingers. Hands like you're high-fiving. Hands flat like this. Yes. Yes. I may have told you this, but years ago when there was a provincial exam, first, I teach my students to do this very obviously, get your hands away from your body. Years ago when there was a provincial exam, students used to have to write upstairs in the library, and the teacher was not allowed to be in the room. Someone else was supervising the provincial. And about halfway through the exam, I got a phone call on the teacher on the other end. Oh, Mr. Dewick, you're going to be so disappointed in your students. They've invented hand signals. They're signaling answers to each other, Mr. Dewick. They've come up with an elaborate cheating scheme. And so I explained, no. They're getting to the right-hand rule questions on the exam. And so from then on, I always explained to whoever was supervising, hey, about an hour in, you're going to see kids doing this. They're not giving any hand signals. They're doing right-hand rule questions. Put your pencils down, look up. So here is our setup, courtesy of MIT. We have here a battery, a car battery, a on-off switch, a long wire, and then a pretty strong magnet. There's a horseshoe magnet right there. Go. It's feeling a force. Which way is it feeling a force, Danica, who's not watching right now? Which way is it feeling a force? Up. Yes? What if we reverse the current? Which way will it feel a force? There you go. Okay? That right there, that force, that's how we have all of our electric motors. Any electric motor is using it. Yes? That's a great question. Can you put that in your back pocket? We're going to come to that in a couple of days. What we're going to cleverly say is, what if instead of a wire, what if we have a rotating loop of wire and hook that up to an axle, and maybe now we can actually, hey, that's an electric motor. And if we hook it up to alternating current, that becomes quite convenient as well. But we'll talk about all that. Very nice. Example 8. An electron traveling to the right enters a magnetic field. Wait a minute. My right-hand rules don't work for electrons. They only work for protons. So an electron traveling right is the same as a proton traveling which way? So it enters a magnetic field. Which direction is that magnetic field? What are those X's meant to indicate? So all of you point your right thumbs in the direction a proton is moving here. That way. Magnetic field into the page. On my screen, down the page. On your desks, you'd be looking at your paper. You would point your hand to your left, because the electron's moving to the right, and you would point your fingers into your desk, and your palm is pointing down the page. What you're actually doing with this, And this is something called a cross product. You're actually multiplying two vectors together. It turns out for vectors, this direction cross this direction is down, or up cross my left is towards me. That's a cross product. Old TVs, remember we looked at the cathode ray tube and we looked at how old style TVs used to work? All they were a bunch of electrons hitting a phosphorescent screen. So if you took a magnet near an old TV, you got some neat effects. Don't do this to your nice plasma screens. You might do some permanent damage. So here's an old cathode ray tube television. Strong magnet. And when we bring it in near the electrons, we're seeing the electrons are definitely being deflected by a magnetic field. Okay. Gabor's eyes just lit up. Let me repeat myself. Do not do this to your nice $2,000 plasma flat screen. You might do some permanent damage. However, if you find an old cathode ray style TV at a garage sale for $5, oh heck yeah, you can have a lot of fun with this. You can see when it gets really close that the electrons get deflected so much they don't even hit the screen anymore. Okay. Fun with magnets. Example 9. Ooh, here's a nice three-dimensional picture. A proton enters a magnetic field along the line shown. What direction is the magnetic force on the proton? You know what? So we're all doing the same thing. Why don't you hold your notes up with your left hand so that they're oriented just like my screen with your left hand. With our right hand, I guess we have a proton kind of going into the screen, so point your right thumbs kind of into your paper. Ooh! Which way do magnetic field lines point? Which way do magnetic field lines point? Right? Put your paper down. Draw some arrows in like this. And you can label that if you want to with a capital B. That's your magnetic field. And now pick your paper up again. Now we got our direction of magnetic field. So we have proton going into the page. Again, sorry for those of you on YouTube that can't see this. Magnetic field going that way. What's the correct answer? A, B, C, or D? Did you say B? It is. Down the page. That's which way your palm is pointing. So page, the palm tells you the force. Looking for a stupid way to remember? The high five tells you the force. The 5 is the force, right? Ooh, here's another one. Example 10. The above diagram shows an electron traveling to the right. I don't do electrons. An electron traveling to the right is the same as a proton traveling which way? So again, if you want to, you can hold your paper up. Oh, wait a minute. Let's draw in the magnetic field. Which way do magnetic field lines point from what to what? So let's draw in a couple of lines just so I can see what's going on here. There's my magnetic field. Really, I should do this, by the way. If I'm being really accurate, because I got another physics teacher here, that's the magnetic field. On the outside, they would be curvy, but we're ignoring those right now. We're just looking at specifically between the magnets. So now, hold your paper up vertically if you want to match my particular orientation here. Proton traveling left. Which way is the magnetic field pointing? So I got to bend. Oh, you know what? Just put my hand down by my waist. That works. Which way is my palm pointing? What's the correct answer here? A, B, C, or D? I can't hear. B? Out of the paper? You're telling me that when you do this, out of the paper? I agree. We're going to practice a bunch of these in case you're wondering. We already did example 11 yesterday, I think. And we did example 12 yesterday. Ooh, 13. A wire between two magnetic poles is shown in the above diagram. First thing I need to figure out, I guess, is which way is the current flowing through the... Well, current flows from positive, so it's going to that way. You know what? Here, current is going to be flowing that way, isn't it? Then we need to draw in the magnetic field line. Magnetic field lines point from what to what? So it'll be that way. There's the B field. Which way will that wire experience a force? Try this one on your own, and then I'll do it up here. But try it on your own first. Gabor, it won't be good if you do get your hand away from you. Okay? Oh, I like Darman. He thought, it might be easier if I hold the paper vertically. Don't be scared to change the orientation of the paper, just so that you're not having to contort yourself so much. So if I was doing this with my vertical board behind me, I would be saying, okay, it looks like we have a current going kind of this way. Well, you know what? Into the page. And a magnetic field pointing to my right. And so I think, answer B, yes? Okay. Hey, you're using your left, or you're using your right hand, never mind. Okay? So that way, thumb goes this way, page. Magnetic field that way, down the page. Is that all right? We need to practice this. This is weird. What was the answer? B? Ooh. A beam of positively and negatively charged particles enters a magnetic field as shown. Okay. Which path illustrates the positive and which path illustrates the negatives? Let's assume that the first beam is positive. Let's assume the positives are moving to the right. What direction is the magnetic field in this question supposed to be? What do those X's mean? Into the page, right? So, now you pointed that way, that only if your paper is up or you're going with my board. So don't be scared to hold your paper up and orient it with my board. So, which way will the positive get deflected? Path 1 or path 2? And then I guess the negative would be the other path. That would make sense to me, yes? So, let's see. That way, ooh. Which path is positive, 1 or 2? Let's follow it. Ready? So let's assume that this is the beam going this way. What direction is the magnetic field pointing? What direction is the magnetic field? What do these X's mean? Okay? Which way is my palm pointing? Positives are going to follow path 1. Negatives are going to follow path 2. So, as always, for these 2-column multiple choice questions, I would say yes, yes, no, 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 yes, no, yes, and then I zoom out and clearly the correct answer is B. Never try and read across, always read down. By the way, if you're finding this tricky, you're normal. This is tricky. We'll practice this and practice this and practice this. You might notice I've got a bajillion homework practice questions too. 15. An electron enters a uniform magnetic field as shown below. The path of the electron upon entering the field would be linear, circular, parabolic, hyperbolic. Well, first of all, which way is the electron moving? So we don't do electrons. What do? Okay, so I would imagine a proton moving to the left. This one here is a trick question. It turns out charges are only affected by magnetic fields when they cross them, not when they move parallel to them. And you'll see why here. I'm going to try and do a right-hand rule. So I would go my thumb pointing that way, and I've told you my hand is in the shape of high five. Which way is the magnetic field pointing? Taryn, which way is... No. Look at the picture. Which way is the magnetic field arrows point? What? Okay. Wait a minute. I want the proton. Which way is the magnetic field pointing? Wait a minute. The only way to do that is not to have my hand in the high five position. This does not work for the right hand rule. It's going to keep moving in a straight line. It's not going to feel any force. Charges only feel a force when they cut across magnetic field lines. What if they cut across at an angle? Did I say angle? Components. We'll look at that a little bit, but I'm not going to do a big song dance. You know what your homework is? It's every question for Thursday. Because you need to practice. I tried to throw a whole bunch of all three right-hand rule questions on your test.